Everybody, I am Sundar Nadathur. Let us talk today about EMCO integration with temporal workflows, specifically about what workflows are, why we need them in EMCO, a, a brief overview of the open source temporal workflow engine, and then how temporal workflows are integrated into EMCO. Please note that this work does not preclude integration of other workflow engines into EMCO. When we deploy an application across multiple Kubernetes clusters, many complex scenarios can arise. For example, um, we may want to migrate a stateful application from one cluster to another. This could be because, say, a 5G user element or UV is communicating with the application in a MEC cluster, and the UV has roamed to a new cell tower where another MEC cluster is closer. The need to relocate the app may also arise if the source cluster is approaching capacity or needs to be brought down for maintenance. Another scenario is that when an application is deployed, its networking environment also needs to be set up. This may involve setting up network policies such as firewall rules in devices outside the Kubernetes cluster. A particularly complex scenario involves infrastructure orchestration. One may want to spin up a new cluster before deploying a set of applications on it. In all these cases, the common element is that we have to perform a complex sequence of tasks, each of which may fail, but the entire sequence needs to be completed reliably. This is what we call a workflow. EMCO can handle workflows using a temporal workflow engine. It is an open source engine that offers resilience and proven scale. We can think of temporal workflows as a set of distributed processes, each of which execute several complex stateful steps. These workflows may run for days or months and may even be cron jobs that repeat periodically. These workflows can be written in many common languages. In a traditional application with a client-server model, the client invokes a service which may be backed by a set of worker processes. Each worker runs a set of tasks. In the absence of a workflow engine, an application developer has to handle the restoration of state when a process crashes, and also handle retries with timeouts for each task, with appropriate retry policies and timeout values for each task's needs. With temporal, the client for a workflow would instead connect to the temporal engine. The engine is backed by a set of worker processes which run a set of tasks. The temporal engine records the state of each task and restores the state in the event of a failure. Temporal also provides a standard way to set timeout values and retry policies for each task. Since temporal needs visibility into workflow state, the workflow code must be organized in two parts: a workflow proper, which is deterministic and is restricted from making error-prone tasks like calling external APIs, and a set of activities within each workflow which can execute arbitrary code that may fail. So in a temporal deployment, we will see a temporal server, a set of worker processes that execute user code, which include both the deterministic workflow parts and the activities which may be not deterministic. The workflow client calls the temporal server to start the workflow and to monitor it. The temporal framework offers many benefits. One is resilience, since the temporal server records the state of each task and restores the state in the event of a failure. It provides a standard way to set timeout values and retry policies for workflows and their constituent activities. It also helps with observability of workflows with status checks and queries, and it is known to scale to a large number of workflows and tasks. Let us now look at how temporal can be integrated with the EMCO. In a cloud-native deployment, the temporal server will be deployed as a container running in one or more Kubernetes pods. The worker processes will also be deployed as Kubernetes pods, perhaps in a different cluster. They may be deployed with a Helm chart across one or more clusters, possibly by EMCO itself. A single worker can execute many tasks for many different workflows. The workflow client will also be deployed as a Kubernetes pod, and it may be in yet another cluster. One pod may contain more than one workflow client, and each client may possibly handle more than one workflow. EMCO needs a way to invoke the workflow client, so we expect that the client is packaged with the HTTP server. This HTTP server takes an HTTP post call to trigger the right workflow client. The workflow parameters are included in the body of the post call. EMCO is composed of many microservices. EMCO may be deployed in a different Kubernetes cluster than workflow clients, work and workflows, worker processes, and so on. Okay. We have added the workflow manager, a separate microservice that allows EMCO users to define intents for workflows, including the workflow client location, as well as timeouts and retry policies for each activity and for the whole workflow. The workflow manager initiates a workflow by doing HTTP post to the workflow client. The workflow manager can also perform status checks and execute queries on a workflow by directly calling the temporal server. It can also terminate or cancel the workflow. The EMCO integration with Temporal has been released in the EMCO 2203 release recently. There is further work planned to launch workflows at specific points in the application lifecycle, such as pre or post deployment, update, and termination of an application. Thank you.